Hey everybody, welcome to your third of my Symbolic Logic classes. Today, I really want to get into the core subject matter of this course. So I want to start out by reminding you that last time um, I introduced you to 5 new logical symbols. And here they are, you can see them on the board right now, or excuse me, you can see them on the screen. Um, These are the symbols for not, or, and, if then, and if and only if, which we sometimes write IFF. All right. And so here's the standard set of symbols I'm going to use. The not looks like a sideways L, the or looks like a V, the and is just your standard and sign, an ampersand. If then is designated with an arrow, and if and only if is an arrow that points both ways. All right, and what I told you last time is that all you need to do to know whether an argument is valid is symbolize it, and then determine whether the symbolization matches an argument that's known to be valid. And I told you the first way we're going to learn of doing this is called natural deduction. And so that's what we're going to start doing today. We are going to talk a little bit more in depth about the words and or, and how we symbolize statements using those symbols. And we're going to talk about some very simple natural deductions. So, natural deduction is a technique of proving something that is probably familiar to you from mathematics. If you've ever done a mathematical proof, what you were doing was something like natural deduction, even though that might not have been what it was called. The proofs that people do in mathematics are often less explicit than the proofs that we're going to be doing in this class. All right. But here's the general idea. To prove that gamma entails p with natural deduction, what we do is we start with a short list of canonical arguments that we already know are valid. And then we demonstrate that the argument gamma therefore p is really just a combination of those canonical arguments that we already know are valid. Okay? These canonical arguments are called inference rules. And we're going to start out by learning 10 inference rules, 10 canonical arguments. And something that we're going to prove a little bit later on in this class is actually that those are all the arguments you need. Absolutely any deductive argument that can be symbolized with the logical connectives that I have given to you can be proven, if it is valid, using only these 10 inference rules. You'll have a better idea of what I mean when I say that as today's video goes on. Okay? But again, the idea is I'm going to give you 10 arguments that are very obviously valid. It's going to be very easy to convince yourself that they're valid. And we're going to have a systematic way of stringing them together so that we can demonstrate that more complicated arguments are really just combinations of these very, very simple ones. All right, I'm going to start out by giving you an actual very simple argument. Here it is. All right, again, as always, premise is blue, conclusion is green. Here's the argument. Cheese is delicious and wine is delicious. Therefore, cheese is delicious. All right, or we could have a different conclusion if we wanted to. We could say, therefore, wine is delicious. Now, this argument is valid, and it's valid for the same reason that valid arguments always are. It is impossible for the conclusion to be false, unless the premise is false. All right, in this case, there's only one premise. But let's think about this for a second. Suppose the conclusion is false. Suppose that cheese were not delicious. Well, then you can just immediately see that the premise is false, because the premise tells you that cheese is delicious. Okay, so this is a valid argument. If the conclusion is false, the premise must be. This argument is very easy to symbolize. Here's how we symbolize it. We let lowercase c stand for the sentence cheese is delicious. We let lowercase w stand for the sentence wine is delicious. And then the argument is just in squiggly brackets c and w, and that entails c. Or, as I said before, if we wanted it to, it entails w. All right, and there's your argument. Now, I mentioned something very important about deductive arguments last time, and an important way that they are different from inductive arguments. With a deductive argument, if an argument is valid, it's valid no matter what the variables that we use to represent different statements stand for. It's valid no matter which letters we use for individual statements, and it's valid no matter what each of those statements actually says. Okay, and so in general, valid arguments are valid no matter what the statement variables stand for. That means we could just rewrite this argument like this. P and Q entails P, or it entails Q, no matter what P and Q are. In other words, the statement P and Q, if it's true, proves that P, or it proves that Q. Okay, and here's how we write that. So look at the last line on the screen, and you see I've written the premises the same way, and I've written the conclusion the same way. But instead of using the double turnstile, the symbol that means entails, I've used a single turnstile, all right? It looks like a sideways T, and that symbol just means proves. All right, so your premise, P and Q, proves the conclusion, P. It proves it because this argument is valid no matter what the statement variables are. Okay. Now, we could have used a slightly different argument. Okay. Here it is. Two premises this time. Premise 1, cheese is delicious. Premise 2, wine is delicious. Your conclusion, therefore, cheese is delicious and wine is delicious. And again, you can see that this is a valid argument, all right? If the conclusion is false, then at least one of the premises must be false, right? So suppose the conclusion were false. That would mean that either cheese was not delicious or that wine was not delicious. Well, your second conclusion says that wine is delicious, so if it's true, the only way for the conclusion to be false is if cheese is not delicious. But your first premise says that cheese is delicious, and so that premise has to be false. Okay, the only way for the conclusion to be false is for one of the premises to be false. So this, again, is a very obviously valid argument. And we can symbolize this argument much the same way we symbolized the last one. We let C equal cheese is delicious, and we let W equal wine is delicious. And then here's our argument. You have the two premises in the squiggly brackets, C and W, and those two statements entail the conclusion, C ampersand W. As before, since this argument is valid, it's valid no matter what the statements are. It's valid no matter what C and W stand for. And so in general, Whenever you have the two premises P and Q, that entails the conclusion P and Q, no matter what P and Q are. And so, P and Q prove P and Q. All right? And that's what I've written here on the last line. Again, that symbol that looks like a sideways T just means proves. Now, this is extremely obvious, I think. It's so simple that you probably wonder why I'm even bothering to explain it. But it's important to actually get clear on this now. There turn out to be some surprising consequences of some of these very, very, very simple arguments. So just bear with me for the time being. A statement that is symbolized P ampersand Q, a statement of the form P and Q, is called a conjunction. And in a statement like this, P and Q are called the conjuncts. Okay? And so what I've just given you are two extremely simple arguments about conjunction. All right? And I'm going to do the exact same thing for the other four logical connectives that I taught you last time. I'm going to give you two extremely simple arguments about each of them. So look at the table on the screen right now, and you'll see that on the left-hand side, I've written down the list of logical connectives that I taught you last time. And then I've got two columns next to that. I have a column for what I've called an introduction rule, and I've got a column for what I'm calling an elimination rule. And in the introduction rule column, next to and, I have written the second of these very, very simple arguments that we just talked about. Okay? P comma Q proves P and Q. This is called an introduction rule because the premises do not have the symbol for and in them, but the conclusion does. And so we have introduced an and sign into the conclusion. And now the elimination rule is just that first argument that I covered with you. P and Q proves P, or it proves Q. Okay? And again, this is called an elimination rule because the premise does have an and sign in it, but the conclusion doesn't. And so we've eliminated an and sign. All right? For the four other rules, we're going to do the same thing. We're going to have one introduction rule, a rule that lets us add that symbol to a conclusion, and we're going to have one elimination rule, a rule that allows us to eliminate a symbol from the conclusion. Okay, so those are your first two inference rules, the and introduction rule and the and elimination rule. When we symbolize ordinary English sentences, there are actually a lot of ordinary English words and phrases that we symbolize with an and sign. All right, it's not just the word and. So, for example, the word and, the word also, the phrase as well as, the word while, even though, although, but, so is, all of these words or phrases are typically symbolized with an and sign. And you can see this if you look at this list of sentences here. All of these sentences are logically equivalent to each other. Okay? If any one of these sentences is true, so are all of the other ones. If any one of these sentences is false, so are all of the other ones. They say the same things logically, but they use different vocabulary. Okay, and they can all be symbolized the same way. You would symbolize all of them C and W. Okay? Both cheese and wine are delicious. Cheese, also wine, is delicious. Although cheese is delicious, so is wine. Even though cheese is delicious, wine is delicious too. Cheese as well as wine is delicious. Cheese is delicious, but wine is as well. Okay? All of those mean the same thing. And so we symbolize them all in the same way. And this is an important lesson, okay? Logic is not about style. Okay? Sometimes when people write, they write in a very persuasive style. The way that they phrase things is moving, or it's powerful, or it's convincing. But when we talk about whether an argument is logical, we don't care about any of that. Okay? All of these sentences, even though they are stylistically very different, they have the same logical content, we symbolize them the exact same way, and we treat them exactly like each other when we're trying to determine whether an argument is valid or not. Now, I've given you two inference rules, and with just these two inference rules, we can already prove a few things that are pretty useful to know, or at least they will be useful later on in this course. And I'm going to give you one example right now. Here's the example. P and Q entails Q and P. Well, how do we prove this? Here's how we prove it. All right. What you see on the screen right now is a logical proof. It is a natural deduction. You can see that every line of this proof is numbered. You're always going to do this when you write a proof. And the very first line is just the premise of the argument. So, line 1 says P and Q. And then on the right-hand side, in parentheses, I've written down that this is the premise of the argument. All right. Line 2 says P. And I've written that down because of what line 1 says. So look at the parentheses on the right-hand side. It says 1 period, and then it says and E. That E stands for elimination. In other words, I have used the and elimination rule and line 1. The and elimination rule says that P and Q proves P. Okay, so line 1 says P and Q. On line 2, I've written down P, the thing that line 1 proves, and the rule that I've used to prove it. Line 3, Q. And again, I got that from line 1 using my and elimination rule. And now on line 4, I have Q and P. How did I get Q and P? Well, the Q is on line 3, the P is on line 2, and I've used my and introduction rule. My and introduction rule tells me that whenever I know that Q and I know that P, I know that Q and P, right? Q combined with P proves Q and P. Line 3 says Q, line 2 says P, so using my and introduction rule, I've written down Q and P. And that's the end of the proof. I wanted to prove that P and Q entailed Q and P, and here I've done it. I started out with P and Q, and on a series of lines, using only the two rules that I've taught you, I've ended up writing down Q and P. That's a natural deduction. Okay, so that one was pretty easy. That was pretty simple. We'll get a more interesting one in a little bit, and then in my next video, we'll start doing some more complicated things. All right, here's another argument. This one does not use the word and, it uses the word or. And here's what it says. Either I'm Chinese, or I'm American. I'm not Chinese, so I'm American. Again, this argument is pretty obviously valid. To see why, pretend the premise is false. Pretend I'm not American. And now look at the first premise. The first premise says, I'm Chinese or I'm American. Well, if I'm not American, that means I must be Chinese, so I'm Chinese. But now look at the second premise. The second premise says I'm not Chinese. So one of the premises is false, right? If the conclusion is false, one of the premises has to be false. And that means this argument is valid. Okay, so we can symbolize it. We're going to let C be I'm Chinese, and we're going to let A be I'm American. And then here's the argument. C or A, in other words, I'm Chinese or I'm American, not C, I'm not Chinese, entails A, I'm American. Okay. Once again, when an argument is valid, it doesn't matter what the individual statement variables stand for. And so we can generalize this argument. It's always valid no matter which statement variables we use. So in general, if we have these two premises, P or Q, and not P, that proves Q. Okay? This is our or elimination rule, right? Because the first premise has an or sign in it, but the conclusion does not. We have eliminated the or. Now, I'm going to use this argument to tell you a story. And I'm telling you this story because understanding the story will help you understand the or introduction rule. The or introduction rule seems counterintuitive to a lot of students, but it shouldn't. It should be obvious to you if you understand what or means in the correct way. So I'm gonna give you a story to illustrate the point. Here it is. A detective is trying to discover who robbed the store. At first, she thinks the cashier must have done it. Later, she realizes that two other people might have done it instead, the store owner or the famous masked robber. So she says this: it was probably the cashier. Otherwise, it must have been either the owner or the masked robber. And she symbolizes her statement thus. And then you can see how she symbolized this. So C stands for the cashier robbed the store, O stands for the owner robbed the store, and M stands for the masked robber robbed the store. Okay? And so her final statement says it was the cashier, or it was either the owner or the masked robber. Okay? The next day, the detective discovers that the cashier could not have robbed the store since he was in Hainan on vacation. Since the detective is a clever logician, she realizes that her first premise, combined with not C, entails O or M, right? So just look at the argument I have written down right there, okay? The first big complicated statement is just the statement from the previous slide. The cashier robbed the store, or else either the owner robbed the store or the masked robber robbed the store. And the second statement says what we just discovered, namely, the cashier did not rob the store. And now, because of our or elimination rule that we just learned, those two premises entail O or M, right? The first premise is a disjunction. It's an or statement. And then we say the first half of that or statement is not true. So the second half of that or statement must be, okay, O or M. It must have been either the owner or the masked robber. But then the detective makes another discovery. The store owner is the masked robber. All right, now why have I been talking about the masked robber and the detective? The reason is this: the detective was thinking logically. The detective reasoned well. The conclusion the detective reached was true. Her conclusion was that it was the owner or the masked robber. And it was. It was the masked robber. In fact, it was both of them. The owner and the masked robber are the same person. Here's why this is important. The conclusion of the detective's argument is an or statement. It says O or M. that statement is true, even though O and M are both true. Here's the general point. When you have a statement, P or Q, that statement is true if P and Q are both true. Now, if you've done any computer programming, this is probably very, very obvious to you. But sometimes students who have not done any computer programming before or have not done any logic before, sometimes at first they think this is a little bit weird. But it's true. And you can tell by thinking about the story I just told you about the detective. Okay? In general, here's what this means. If P is the premise in an argument, that proves P or Q, and it proves Q or P. And here's why. Imagine that the statement P is true, and then you have some other statement Q. Well, Q is either true or false. And if P and Q are both true, then, like we just said, P or Q is true. Well, suppose P is true and Q is false. Well, then it's still true that either P or Q, because P is true. Okay? So, the statement P proves the statement P or Q. Okay, it also proves the statement Q or P, because that means the same thing. In other words, OR is not exclusive. Okay, it's not exclusive in logic. In fact, it's not exclusive in ordinary English either. Okay. Now, a statement of the form P or Q is called a disjunction. You probably heard me say this word earlier in the video. A disjunction is just a statement that you symbolize P or Q. And then P and Q are called disjuncts. Okay, so if a statement is P and Q, it's a conjunction. If it's P or Q, it is a disjunction. If you have a conjunction, then P and Q are called conjuncts. If you have a disjunction, then P and Q are called disjuncts. And so now we have four rules, right? We have an introduction rule and we have an introduction and an elimination rule for conjunctions, and we have an introduction and an elimination rule for disjunctions. Okay, and there they all are. I've just rewritten exactly the rules that we already talked about. And again, in an introduction rule, the conclusion has a logical symbol that the premise is missing. In an elimination rule, the premise has a symbol that the conclusion is missing. Now, the English words or and otherwise are both typically symbolized with the or sign. But you need to be careful about the phrase neither nor. Neither P nor Q is symbolized not, parentheses, P or Q. It is not symbolized not P or not Q. This is super important to realize, right? If I tell you I am neither Chinese nor American, that does not mean either I'm not Chinese or I'm not American. It means I am not either Chinese or American. Okay? And so you got to remember this. Whenever you see neither nor, the not applies to the entire disjunction. It does not apply just to the disjuncts. Now, with the four rules that I've given you, we can already prove something that's pretty interesting. And here's what it is. P and not P entails Q. Okay? I'm going to do the proof real fast, show you how this works, and then I'm going to talk for a little bit about what this means. So here's the proof. Line 1 says P and not P. And again, on the right-hand side, I've indicated that that's just the premise of an argument. Line 2 says P. And that comes from line 1. I just used the and elimination rule. Line 3 says P or Q. That comes from line 2 from the or introduction rule. Remember, P proves P or Q. Line 4 says not P. That comes from line 1, from and elimination. And line 5 says Q. That comes from lines 3 and 4, from the or elimination rule. So remember, if you have a statement that says P or Q, and you have a statement that says not P, those two statements together prove that Q. All right, now I want you to think carefully about what this means for a minute. This argument only has one premise in it, P and not P. That premise does not even mention Q. But I've still been able to prove Q. Okay? Q could be anything. It could be anything at all. It can be something that is completely unrelated to the premise. But I've just proven that if the premise is true, Q is true anyway. Now, there's a very important lesson here. Statement 1 is self-contradictory. It says that the very same statement both is true and is not true. And here's the important lesson. If you ever accept that a self-contradictory statement is true, then you are logically committed to believing absolutely everything. Okay? This is an excellent reason to think that self-contradictory statements can never be true. All right? And if you lose sight of that fact, okay, if you lose sight of the fact that if P is true, then not P is false, then you end up being able to prove absolutely anything, absurd things, right? Q could say, unicorns and dragons live in Spain. And if P and not P were true, I could prove that. All right, now, an idea that's similar to this one is going to be very important in the next video. All right, and so I wanted to show you this argument now so that when something similar comes up next time, you won't be surprised. All right, but you can see this is a perfectly good argument, right? We have 4 inference rules. All 4 of them are very, very simple and very, very obvious. And I've just combined 3 of them to prove that this argument is valid. All right. That's pretty much all that I wanted to cover today. Next time, I'm going to give you introduction and elimination rules for the not sign, for the if-then sign, and for the if and only if sign. Okay? And after I've given you those rules, we'll be able to do some more complicated arguments, and I'm actually going to give you some homework problems after that. All right? So I hope you enjoyed this video, and I will see you next time.